sit at the table because I have lots of demos and cool graphs to show you, and I want to focus on that. But I promise I'll stand up at the end so that you can ask me questions. So my name is Elena Popovici. I'm a computer scientist through and through. All my degrees were in CS, and for my academic research, I did stochastic optimization, in particular evolutionary algorithms. In terms of industry experience, for the past 7 years, I've basically been in the business of applying computer science to real-world problems. I work for this company called Ecosystem. It's a US company. It's located in Cambridge, Massachusetts, which is just outside of Boston. And what we do is we're part scientific business consultancy and part idea incubator. And we basically try to help people in organizations understand how complexity can come from simple interactions. So to do that, we use techniques like modeling and simulation, data analysis and visualization, network science. And then once you have that kind of understanding, is that going to be better? Okay.
Put your hand
Should I put this? Is this going to work? Do you hear me?
Yeah.
Okay, great. Thanks. Right, so once you have that kind of understanding, then the next step is to make better decisions. And for that, that's where the stochastic search and optimization comes into play. So just a few quick examples of application domains: pharma, anything from pharma to engineering design to log network analysis and many other things. We do this for Fortune 500 companies, international companies, the US government. In terms of the idea incubator, we have both business products, like a tool for chemists, a tool for marketing, agencies. Nibbler is a cool baby name finder. And Infamous, something I encourage you to check out, is basically a cool way to create your own dynamic, interactive word clouds of your favorite online content. And there's many other demos and cool things to play with on our website if you want to check it out. It's just ecosystem.com. But let's move on to today's topic. So, exploratory data analysis. We're going to cover it via an actual case study. So I'll go over in this order process, insights, and tools. But really my main message to you is going to be about the process. And I want to give a little bit of credit here. The inspiration for the framework that I'm going to use for today comes from Jeff Leake's data analysis class on Coursera, which, if you're a beginner in data analysis, I strongly recommend it. So I said process. What are the data analysis steps? Well, coming from an empirical analysis, computer science background, the typical steps that I've been taught are as follows. You start by defining a question or a hypothesis. You design some kind of experiment, or you define an ideal data set that will help you answer that question or hypothesis. Conduct the experiment, collect the data, and only then do you actually get to the analysis part. Now, one trend that's been happening in recent years is that, people started doing away with number 1 and number 2, and jump straight to collecting data. So, why is this happening? Like, why do people collect data without a particular question in mind? Well, there can be two kinds of reasons. One of them is just, well, because we can. We couldn't 10, 20 years ago, but now we can, so let's just collect it, then we'll figure out later what to do with it. But there's also regulatory reasons. So there's various government organizations that are actually required to document their activities, but they're not told ahead of time, what people are going to want to look into. And today's case study is actually an example of that. It's some data from the US Medicare organization, which is basically like the MSP here, except that it's mainly for seniors and some people with disabilities. Now, data collected this way can still be useful, but it's less than ideal. There are some consequences to the fact that you didn't start out with the question. So let's see what these are. I'm going to start with what you can do with properly collected data, and then we're going to start crossing out something. So you can describe a population. If you have data, you can explore it to find maybe some relationships you didn't know about. You can infer from a small sample something about a larger population. You can predict values about unseen objects from data about other objects. This is basically the realm of machine learning. You can try to establish cause, what happens to one variable and change another. And then the most sophisticated one is where you actually establish via what mechanism does that change occur. Now, if you have just collected data, if you haven't performed an experiment, you have what's called observational data. And with observational data, you cannot do causal or mechanistic analysis. So those two are immediately off the table. Now, in principle, you might still be able to do some inference or some prediction. But what happens is that a particular data set may still not be able to answer the specific question that you have if it was not designed to do so. And since, inference and prediction are a lot about testing hypotheses, often you might not be able to do them with a particular data set. It doesn't matter, you can do them in general, but, for instance, maybe the variables that you need haven't been collected, or maybe sampling hasn't been done properly, or maybe the data has been aggregated too much. And all of those things could be things that might prevent you from using a specific data set to answer a specific question. So we put a question mark there, and then we focus on what's left, which you can pretty much do with any kind of data. And that's exploratory analysis, which encompasses descriptive as well. So what is exploratory data analysis, and why can you pretty much always do it? Well, because it's open-ended. You don't start out trying to prove something. You start out looking for something when it's something you didn't know before, right? And you're looking for something interesting, which is in the eye of the beholder, so you're only going to know it when you see it. Right, so it can be defined ahead of time. And by doing all this, you actually start to form those hypotheses that you didn't have at the beginning, right? You start to raise questions, you start to generate leads. What all of this means is that to be able to make any definitive statements, you inevitably are going to have to define future studies and collect new data in order to answer those questions and test those hypotheses. Because exploratory data analysis is never the final say. Okay, and it is not to be used by itself for inference, prediction, or causality. You're often going to hear, that correlation does not imply causation, but in fact, correlation alone doesn't even give you inference or prediction. It's not sufficient for that. All right, well, enough talk about what you cannot do. Let's talk about what we can do and about how we do it. So here are typical steps of a data analysis. We have those two that may or may not have happened. And then we have the data collection. And in fact, often you might actually deal with data that was obtained by some other third party. So one additional step there might be to understand what is in this data that someone else may have collected. Then once you have the data, you have to check it, process it, clean it. These things are usually referred as data munging or data wrangling. And it's only then that you get to explore it. If the data is proper for it, then you might do some statistical modeling and prediction. And by the way, you should have noticed this in Kazem's talk, right? Because he started out with statistics about his data, right? So in some sense, he did some exploratory data analysis before he did machine learning. Regardless, afterwards, you have to interpret the results. You should challenge those results, especially if they look unusual. And you need to communicate the results. Now, this process isn't always linear. Often you have to cycle back. Oh, and very important, along the way, create reproducible code. I'll come back to that. But the iterative stuff, right? So you go through these steps, but often you might have to go back. You might have to go. Once you interpret results, you might go back and explore some more. Every now and then, you might even have to go back and do some additional munging, or you might even have to go back and understand something additional about your data. So we're going to focus on the exploratory step, but we're also going to touch on a couple of other ones. And in particular, we're going to start by understanding what's in our data because it was collected by someone other than me. Well, you obviously are not very familiar with what's in it. So here's the data. It basically contains records from 2011 from all hospitals in the US that bill the Medicare program. It has information about for which diseases did they bill the program and for what amount. And it's a relatively small data set. It has about 163,000 rows. That's not a lot. And it only has 11 columns. So, when people talk about big data, usually they tend to refer to the number of rows. And this is not big data by that standard in any way. But what I want to show you today is how complexity can actually come from the columns, right? I'm not arguing that the big data row thing is not a problem. It's definitely a problem. But I want to show you yet another problem. So it can come from the columns, even when they're very few. So let's start by seeing what they are. So there's 11 of them. We have hospital ID, name, bunch of geographic information, street, address, city, state, zip code. There's something called the referral region. Then we have the stuff about the disease in the form of something that's called a diagnosis-related group. It's a code. I'm going to refer to it as the DRG just because it's really short to say. But it's basically a group of diagnoses. And then for every pair of a hospital and the DRG code, the data contains how many discharges did the hospital charge for that diagnosis. And it also has some financial information. It has, what is the average per discharge amount that the hospital billed Medicare. And it also has the average per discharge amount that Medicare paid back to the hospital. Now, let's trim this data down a little bit. I said 11 is not a lot, but we're going to reduce it to even less than that. So we're going to take those two, just refer to it as the hospital. Then the next ones, they're basically geographic information. We're going to refer to it as that, just as that, the hospital's geo, and mostly I'm just going to use the state as a representative. So if we do that, then we're down to 6. But I want to cut some more. So let's look at the money columns. Now, the main reason there was a lot of excitement in the States when this data was first released is because there was interest in understanding what must senior pay for their healthcare. Unfortunately, this data turns out not to be very adept at that, and that's for two main reasons. One of them is that there are some interpretability issues. Now, the total payments, that's fairly clear. It's money that changed hands. Medicare gave that amount to the hospital. However, the charges are nowhere nearly as simple. In particular, they didn't change hands between two parties. Some of it are made up by the reimbursement from Medicare, but some other parts, may have been paid by the patient. Some may have been reimbursed by the patient's insurance to the hospital, but then there's a complex relationship. Insurers can have all sorts of deals with hospitals. Some of it may have ended up even being written off. So even if we were to look at the data and find something interesting in it, it would be very hard to interpret what exactly does that mean. Now, the other problem with the money columns is the business of aggregation, right? So they're averages, and we have no information about what kind of distribution is behind those averages. And I'll show an example of how that can be very important. So I decided to drop the money columns, and with that, we're down to 4, now much simpler. You're going to say, well, what can be so complex in 4 columns of data, what I'm going to argue is that the complexity comes from the fact that this data is in fact relational data. Okay, what do I mean by that? Well, we have a bunch of entities. We have hospitals, we have the diagnosis, and then we have the geography, right? Now, a hospital is only in one state, but a state can have many hospitals, so it's a one-to-many. Then a hospital has a certain number of discharges for a particular diagnosis. A hospital can handle multiple diagnoses, and conversely, a diagnosis can be handled by multiple hospitals. So that's our relational data, and I'm going to argue that because it's relational, it's rich. And why is that? Well, it's because by aggregating over those relationships, we can actually come up with many additional interesting properties of our entities. So let's see what I mean by that. And we're going to start with the hospital. So, if we look at one hospital can handle multiple DRGs if, well, the very first thing is we can count how many, right? And we can think of that as a property of the hospital. It kind of gives us an indication of, is it a specialized hospital? Does it handle only, a couple of them? Or is it a generalist hospital? Does it handle many of them? We can then sum over all the DRGs, the number of discharges to get a hospital total, and that's going to be an indication of is it a small hospital or is it a large hospital? Then we can also try and look and see for this hospital which DRG is the most prevalent one, right? Like for which one does the hospital have the most discharges, and what is the percentage that is for that top DRG? And these two are also sort of an indication of a specialization if the hospital has any. Conversely, for the DRG, we can look and see how many hospitals cover it, handle it. That's sort of an indication of coverage or perhaps prevalence. We can sum the total number of discharges over the hospitals, and that's definitely an indication of prevalence of that diagnosis. We can again identify things such as what is the hospital with the most discharges. That's kind of a notion of incidence. And we can take these properties and actually also compute them for a particular DRG and state pair, right? If we just, instead of aggregating over all hospitals, if we just aggregate over the hospitals in one state, we can compute the same properties for that particular state. So what about the states? What properties might they have? Well, again, we can now actually traverse two relationships in our relational graph. So we can get total number of discharges in the state. We can count how many hospitals. We could even see if all DRGs are handled in the state or not. And these things can be indications of sort of coverage of diseases. It can be an indication of perhaps health in that state, but it might also be an indication of perhaps culture. Maybe in some states people tend to go to the hospital more when they're sick, and in other states they might just stay at home, and so on. And you could then again identify special hospitals or special DRGs, maybe ones with most discharges, least discharges, and so on. So if we now pull all of these properties together, you might start to think that okay, there were 4 columns, but there's really a lot of stuff going on in this data. It's just waiting there for you to explore it. And hopefully with that, you might start to see some of the challenges of exploratory data analysis, because I mentioned that it's about finding relationships you didn't know about. Well, now there's going to be a combinatorial explosion of relationships that you might want to investigate. And then I also said, you don't know until you look at it, until you see it. You don't know until you see it whether it's interesting or not. So there's the element of human reliance to explore all of that. But we know what we're up against, so okay, let's move on. We did our understanding. Next comes data munging. Okay, this data was relatively clean, but here are some typical operations you might have to do. Even if it's clean, you still have to check to find out whether it's clean or not. So there's checking dimensions, checking and fixing column names. You always have to do something about transforming the type of the columns. Now, R, if you use R, is pretty good at that, but with categorical and textual, it might need your help a little bit. Very important, identify whether there's any missing data. Luckily there wasn't, but if there is, that's challenging to deal with. Inconsistent value, check ranges, units, etc. Then you might need to reshape your data set or create new variables. Well, yes, I actually had to do a lot of this. Why? Because of that, right? Like we came up conceptually with all of those properties, but you actually have to write code to compute them. And you can do it different ways. You can add columns to your existing data table, but you might be duplicating a lot of information. You might not want to do that, even how many rows you have. So conversely, you might actually create additional data tables. Like you might create a hospital table and a state table and a DRG table. And finally, one last step is you might need to merge data sets. Like you might need to actually have to pull data from different sources, and I'm going to show some examples of what I did actually have to do some of that. Now, anybody that's ever done data analysis is going to tell you this. Data munging takes a lot of time. Again, it's important that it be reproducible. And a few notes on that, save a copy of your raw data. Save a link to where you got it from. Sometimes it's good to actually save the date when you got it, because some sites actually post lots of data and they might, it might disappear, it might change, and so on. And record all of your data munging steps in code. In particular, don't just go in Excel and manually edit cells. That's not reproducible. Alright, so let's check that off as well. Finally, we're at exploratory data analysis. How do we do that? Well, we make a lot of plots. Okay? It's a lot about visualization. Why do we make plots? Well, we make plots to understand data properties, to assess variability, to find patterns or regularity, but also, conversely, to find irregularities or to find things that stand out in the data. We might do it to suggest modeling strategies, look at some plots to see if that linear model really is a good idea or not. And sometimes you can actually use it to debug your analysis. Now the plots that you make for this set of goals, they're called exploratory plots, and that's to contrast them with what's called expository plots. Expository plots are what you make specifically with the goal of communicating results. And these two kinds of plots, they don't just have different goals, they actually are very different in the way that they look and in the way that you make them. So I want to go a little bit over that. Exploratory plots are most of your plots. You're going to make tons of them, thousands, hundreds, and you're going to make them very quickly. So out of all your budgeted time, you're not going to spend, the equivalent of 99%, maybe only 60, 70, something like that. They're supposed to be understandable by you. They're supposed to convey information to you. You don't need, when you make these, you don't need yet to worry about someone else. So, because of that, they might have rough axis labels and legends. The various visualization channels like color, size, position, etc. You use them for information only. And here's a personal bit of advice. Try not to link them. If you give somebody an exploratory plot, they tend to run off with it, and you might not get a chance to make an expository one. And your visualization skills might still be judged as if that was supposed to be expository. So what about expository ones, right? Like you're going to make only a handful of those, 1, 2, 4 of them tops. You're going to make them carefully. Okay, they're going to amount, those 3 plots are going to amount for 30% of your plot making time. And the reason for that is because they need to be understandable by and informative to other people. And therefore, they need to be self-contained. So between your axis labels, legends, title, caption, they need to stand on their own. You're not going to be there to explain them. That means, you need to make all the information sort of large enough to be visible, legible. You should use natural language and not variable names from your code. And now those visualization channels like color and size, you're going to use them not just to convey information, but you should try to use them to ease the speed of perception and as well as for aesthetics. So, for the remainder of this talk, but before I do that, I saw a couple of people taking notes. I forgot to mention at the beginning that I will make the slides available online, so you don't need to worry too much. Everything I say and show is going to be available. Alright, so for the remainder of the talk, I'm basically going to kind of walk you step by step through the process, and therefore I'm going to show a lot of exploratory plots. Okay, I'm going to show only a very small selection of everything that I made, probably less than 1%. I made something around, 2,000, 3,000 plots. It took about half a gig on my hard drive. For comparison purposes, the data itself only took 25 megs, okay? I'm only going to show exploratory plots, okay? I'm linking them, I'm disregarding my own advice about linking them. I'm doing that for illustration education purposes only. Some of them will be slightly more polished than what a typical exploratory plot might look like, but I'm actually going to show some really raw ones as well, just to give you an idea. But yeah, by all means, they're not expository plots. And the way that we're going to do that, we're going to use that diagram for reference, and when we make plots about some of these properties, we're going to check some things off of the diagram. And in terms of the goals that we're going to do this with, we're going to focus on the top 4 ones. And even more specifically, most of the time we're going to look at assessing variability and at finding irregularities. Rather than finding patterns, we're mostly going to look to find irregularities. So let's get started. We're going to start with the hospitals, and we're going to look at the number of DRGs, the number of diagnoses that a hospital handle. And we want to get an idea of variability to start with. So one of the greatest, easiest way to do that is a histogram, and again you saw Kazem use that as well. So here's what it looks like, okay? Basically on the x-axis you have how many DRGs per hospital, and on the y-axis how many hospitals handle that particular number of DRGs. Now this histogram seems to suggest, if we need to interpret it, right? It suggests that most hospitals either handle very few DRGs or they handle a lot of DRGs. And it's also a great example of a case where the average would be misleading, right? The average would be somewhere around 50, and you see that that's where the smallest bars are. So aggregation via average, remember that that has its issues. Now, the property we're exploring here, number of DRGs per hospital, is actually discrete, right? Like it only goes from 1 to 100. Those are the only values. So in this particular case, the default R bins for the histograms, they're not ideal. Most of the time they are, and I recommend using them rather than tinkering with them. But since this one is discrete and doesn't have a lot of values, it's better to actually use the exact bits, right? Make 100 bits from 1 to 100. Now we see that our histogram, which we made for the purpose of assessing variability, actually also makes something stand out. What does it make stand out? We have this whole bar here at 1. What does it mean? There's some 90-something, close to 100 hospitals that handle a single DRG. We're going to call them dedicated hospitals, right? They're basically dedicated to a single DRG. But the moment you look at this histogram, you immediately want to know, well, what are they? Where are they? What DRG are they doing? And so on. So let's do that. We're going to bring in a little bit of geographic information, and we're going to put them all on a map. And by the way, this is going to be the only time that I'm going to stray from using just the state for geographic information. Actually, what I did here is that I took the address of the hospital, and I actually did some merging about the data. I cross-referenced it with some Google stuff to get longitude and latitude, so I could put these hospitals precisely on the map. So we have what we have. We have 1 dot per hospital. The color represents the DRG that the hospital is dedicated. So this is not all the hospitals in the US, okay? This is only the 90 or something that are dedicated to a single DRG. You might notice that you can't read the legend. That's because it's not an expository plot, it's an exploratory one. I didn't take the time to make the text large, but don't worry, because I'll help you interpret what's in here, okay? So, and by the way, the colors are not great either. There's like a whole bunch of reds that are very similar to each other. You will be able to tell them apart. But even then, like, this was the first try at this plot, and even like that, it already told me a bunch of stuff. There's that big dot over there. It turns out that it's a hospital in Massachusetts that handles alcohol and drug abuse only. The other thing that you might notice is that there's a lot of this bluish cyan, whatever color there is, that are scattered all over the US. It actually turns out that there's about 47 of them. They are for major joint replacement. Okay? Now, how do we interpret this? Well, maybe it's not so surprising. This is Medicare, which is for seniors. But there are actually also critics in the US that say that, you know, there's some unwarranted use of, artificial hips and other surgical implements and stuff like that, and that it's actually the thing that is driving the costs of US Medicare and so on. Now the thing is, the data can't actually tell us whether the usage is warranted or not. There's nothing in there about that. All it can tell us is that there is in fact some usage. So with this map, we've started to check off some additional things off of our diagram, right? We've looked at a bunch of geo. We've looked, I may have forgotten to mention that. The size, the reason that dot was so large is because the size of the dot was the total number of discharges for the hospital. Sorry, I forgot to mention that. So the total number of discharges, which in this particular case, it's actually the same as discharges for a particular DRG because these were dedicated hospitals. And in some sense, we've also looked at the DRG with most discharges, also because it's dedicated, so it's just that one. So to recap a little bit, what we've done is we started with a histogram to see variability. It also made some stuff stand out, and we followed up on that stuff with a different kind of plot to look at it better. So histograms are great. I recommend them, and we'll see some more usage of them later on. But now another plot that's actually very good for making stuff stand out is a scatter plot. And the reason for that is because instead of collapsing a particular property into those bins, it actually represents the entities and their properties explicitly. Let me show you what I mean by that, okay? So this is a scatter plot of hospitals. You can see, I think this is the only one in this talk where I actually still have the R variable names on the axis, so I'll have to help you interpret what that means. So every dot is a hospital. On the x-axis, we have how many diagnoses does the hospital handle, so it goes from 1 to 100. The color represents which DRG has the largest percentage of the hospital's discharges. In some sense, which is the most prevalent DRG in that hospital. And on the y-axis, we have the associated percentage for it. Right? So in terms of our diagram, we're covering only hospitals and we're showing 3 properties of hospitals at the same time. If we were to use size of those dots, we could have put on a 4th property, but we haven't for now. So let's see, some intuition about this plot. What's going on? Obviously, it has a very distinctive shape, right? Let's actually start with the points in the top left corner. So, basically, if you handle only one DRG, then the percentage is always going to be 100, right? Because all of your discharges are going to go to that DRG. So those 90 hospitals that we saw scattered all over the map, well, in this plot now they're condensed, they're all overlapping in that one point at the top. I wanted to point this out because overlap, even though scatter plots are quite useful, overlap is a common issue with them, and you have to keep that in mind. Now, you'll see that there's a smooth line that I put on this plot in addition to the dots. That line is the 1/n curve. Why is that? Well, because think about it. If a hospital handles n DRGs, and suppose that they would be equally distributed, then each of them would amount for 1/n of the total discharges in the hospital. Now, of course, diagnoses aren't equally distributed, but what it does mean is that the one that's most prevalent, its percentage is always going to be larger than 1/n, right? So, and indeed, you see this in the plot, right? Because the dots follow the trend of the 1/n line, and they're all above the 1/n line. So, the interesting hospitals in this chart are basically the ones that stand out from the crowd, right? Like we have lots of them down here, there's nothing really special about them, it's what we expect. But what about all these ones, like we have that cyan color again over here. If you look at it, they handle 20 or more DRGs, but more than 50% of their discharges come from a single one. Okay? To me, that's kind of interesting, right? Like they do more than half for one, but then they still do like 20 different ones. What is that about? And what DRG is that for? Like, is that color really the same thing? Like, there's 100 colors on this plot, okay? It's an exploratory plot, there's 100 colors. We don't even know if those are for the same thing or not. And we can't even really tell, like, which hospitals are they. You can do that from a static plot in R. You could do it with a bunch of code to extract them manually and so on, but what I decided to do actually was to just build an interactive visualization of this. So I'm going to switch to that. There we go. So this is basically the same plot that we had static, except now it's in a web page, and what we can do is we can hover over the dots. So that's kind of nice. So let's see. Well, we have a bunch of yellow here as well. If we hover over them, we see that they're all. So you can, when you hover, first of all, you can see the name of the hospital. You can see city and state. You can see the exact values for its position, x-axis, y-axis, and then you can see what the color means. So you see that, the most prevalent DRG in this hospital is major joint replacement. And we can see that really all of those yellow ones, all of them are like major joint replacement type stuff. And let's look at the ones we noticed in the first place, which is this sort of batch of dots over here. First of all, is that blue really the same DRG? Well, psychosis, 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 psychosis. All of them are. You can take my word for it. All of them are for psychosis. So they're basically doing between half and 3/4 of discharges are for psychosis, but they also handle like 20 to 50 other things. So you might wonder, well, are there many other things that are related to psychosis that they do? Go sit at the table because you can now look at the controls here on the left. I've added the option to be able to color not by the most prevalent DRG, but by the second most prevalent DRG. It's kind of a proxy for, are the other diagnoses they handle related. So now we can hover over them again. We see cellulitis, alcohol and drug abuse, well, maybe some relationship, pulmonary, septicemia, bowel, septicemia, major joint replacement, pneumonia. They don't seem to really have anything to do with psychosis. Now, to me, this was interesting, and I wonder, like, why is that? What's up with these hospitals? But there's really nothing else in this data help answer that kind of question. I mean, this is one place where you actually, the data help to formulate a question, and now you kind of have to go and do some investigative journalism, some field research, go Google all these things. I actually did Google a bunch of them, just from their front pages. I couldn't really tell much. So you'd have to invest some time to actually look outside the data and to find the reason why. Okay? That's going to be.
How do the second most discharges have more than 50%?
The y-axis hasn't changed. Only the color has changed.
Oh, okay, the color.
Yeah, because I wanted my dots to stay in the same place so I could find the hospitals.
Makes sense.
Yeah, only the color has changed. Thank you. Okay, so now this plot again, it's cleaned up a bit, okay? I put some information on this page about it and stuff, but it's not a great candidate for an expository plot, again, because we have the overlap issue, we have the color issue, and so on. But as an exploratory plot, it served its purpose really well. It helped us uncover some peculiar facts. And while we made it to look at hospitals, it actually kind of started to point out some diagnoses, some diseases, right? Like we saw the major joint replacement stuff and we saw the psychosis stuff. But let's look now more specifically at diseases. So I'm going to switch back to my presentation. Okay, so we're going to start with the number of hospitals that handle a DRG as a sort of a measure of prevalence/coverage. And we could do a histogram, but we basically have only 100 entities. There isn't really a whole lot of points to collapsing 100 data points into a histogram. You can just look at them, like at all of them, by making a bar chart for that particular problem. And it looks kind of like this. Again, I don't expect you to be able to read that stuff. Hell, even I can't read it, which is a slight problem. But basically, this is a fairly straightforward plot, but it helps you do a couple things. It's going to help you identify some of the top ones. Heart disease is in there, and it's going to help you identify some of the bottom ones. Psychosis is actually the last one there on the list. And the other thing about the plot is that it's a very versatile plot. We have it now. What we can do is we can actually break down these bars by various categories of hospitals. Right? Like right now they count hospitals, but if you use properties of hospitals, we can break down the bars. So let's see, what properties might we consider? Well, we started with this notion of how many diagnoses does a hospital handle. We can kind of flip that on its head and split the number of hospitals of a DRG into, how many handle one DRG, how many handle two, how many handle three, and so on. We could also look at just the special case of how many handles one. I handle one to kind of get, for a particular disease, how many dedicated hospitals does it have, right? Like that's something kind of interesting to look at. You might also take the DRG with most discharges in a hospital and flip that on its head and say, well, for a particular diagnosis, in how many hospitals is it the most prevalent one, right? So you might notice that what I'm doing here is I'm actually adding things to my data diagram. Now, this basically means that what we're doing is we're iterating back to that step about understanding the data and about munging the data in particular. Why? Because I'm going to have to, go back and write some code to compute all of these new properties that I've now figured out. And this is common in data analysis. You often don't think ahead of time of everything. But when you do think of new stuff, it's a good idea to try and keep track of them, add them to your data diagram. So the reason I did this though was to take that bar chart and start breaking it down. So we're going to start by breaking it down by in how many hospitals is the DRG the most prevalent. So this is the same chart except that now the length of the red bar is in how many hospitals is the DRG most prevalent, and the length of the yellow bar is in how many hospitals is it not. So if we look at some of the DRGs with many hospitals, the one there with the big red thing is major joint replacement, okay? And if we look around some of the ones with few hospitals, the one with the big red bar at the bottom, psychosis. Now, this basically what it does is that it confirms some of the things that we were only hinted at by that exploratory plot that we made for hospitals. Now, what else could we break this down by? Well, we could break it down, as I mentioned, by how many hospitals do 1 disease, 2 diseases, 3 diseases, and so on. Now, you may notice it's basically like a big smooth gradient. So if you squint, maybe you can see some things that kind of break the monotony on the bottom. Well, is there something we can do to maybe make them stand out? We can do a coarser gradient rather than put one shade for every number. We're now going to use red to mean dedicated hospitals. How many dedicated hospitals are for the DRG? We have 2 shades of orange for sort of specialized hospitals. They either do 2 to 5 or 6 to 20. And yellow we're going to call generalists. They do more than 20 things. So now you can actually see that, you know, those things on the bottom, they weren't an optical illusion. They actually do stand out. And if you were to read the names, they would be things like spinal fusion and back and neck surgery and some other kinds of surgeries. Basically, all things that kind of have to do with like bone type stuff. And the interesting thing about them is that they have no dedicated hospitals. They have only specialized hospitals. So one hypothesis here might be that that this is like a group of diseases and that all these hospitals are the same hospitals that handle all of them. But you'd have to do some more data crunching to figure that out. Now you can also look at the dedicated hospitals. The red doesn't stand out very well here, but basically what it would indicate would be again major joint replacement at the top, and the other one that would stand out somewhere here at the bottom is alcohol and drug abuse. And this is again something we kind of saw on that map that we made very early on of just the dedicated hospitals. There were lots of bluish dots, that was major joint replacement, and then there were a bunch of black dots, that was alcohol and drug abuse. So you can find the same facts via multiple perspectives, and I'm going to argue that that's a good thing, and it's something that you want to do multiple perspectives. Now, but what I also want to argue is that maybe these. This one in particular might not be the best way to convey how different diagnoses differ or are the same. In general, just because an exploratory plot helps you find the fact, it doesn't necessarily mean that you should just clean it up and use it as an expository plot. That's not always a good idea. You got to really think about what it is you're trying to communicate, and often you're going to end up designing something completely new from scratch. And in fact, I'm going to show you something that I think conveys the idea of the fact that there are different kinds of diseases out there better than this one does. But this was the inspiration, because this billing thing is basically reminiscent again of making histograms. So how about we summarize stuff with a histogram? Remember this one at the beginning, we took all the hospitals and we put them in those 100 bins. But we can do the same, but we can do it one disease at a time. Okay, so this in particular is for extracranial procedures, right? Obviously, there's fewer hospitals because not all the hospitals handle it. We zoom in a little bit and we add some color, looks a bit nicer. Now, the color doesn't actually encode anything new. I just it goes from red on the left for specialized hospitals to yellow on the right for generalist hospitals. And the reason I do that is because it's going to help us visually when we put all the DRGs together. Okay, so this is a matrix. It has 100 cells. All the DRGs are in there. And you might start to immediately pick up the fact that there are different style histograms. Like this histogram thing is kind of like a signature of the DRG, if you will. And you're going to say, okay, so there's the one that don't really have much red, which means they're not handled by many specialized hospitals, if any. And then you have the ones that have a lot of red, that are DRGs that are handled by a lot of hospitals. And maybe if you spend a little bit of time looking, you might notice some other ones that, they're kind of like the no red, but then they have a spike on the left. Now this is an example. I mentioned that, exploratory data analysis is very heavy heavy on human reliance, but there are opportunities for automating stuff. So now that we've observed this kind of stuff, and we can kind of formalize it, right? Like, what's interesting here? Interesting is red on the left, right? Well, we can, these are histograms, right? Like, we can count exactly how much stuff is on the left. And if we sort this matrix by that, then it looks like this. And now it's a lot clearer. Okay, I've actually used a slightly more complex criteria than just how much red on the left. I also looked at, is it kind of going up or is it going down? Which made the ones with the spike stand out. But now you can get a much better idea of the different types of DRGs, and there's a kind of a smooth transition from the ones that do lots of, that are done by lots of specialized hospitals to the ones that aren't done by specialized hospitals. And in case you're wondering what those 400 codes across the top are, they're basically the same ones we saw in the bar chart. They're like spinal fusion and back and neck and stuff like that. Major joint replacement is this 470 over here. It has both a lot of specialized and actually a lot of dedicated. And those other two things, alcohol and drug abuse and psychosis. Okay? So I would argue that this might actually be a better candidate for perhaps turning into an expository plot if what you were trying to convey is the fact that, you know, there are different kinds of diseases out there in terms of the nature of the hospitals that handle them. And the other thing about this plot is that it's actually very versatile. Like, you don't necessarily have to have a histogram in there. Like, if you come up with some other kind of visualization that's DRG specific, you can put that in the cell. And here's an example. When instead of a histogram, it's a scatter plot. So basically now, rather than collapsing one property of the hospitals into a histogram, you can actually see all the hospitals that handle DRG and see two properties of them. I'm not going to go into the details of the stuff in here, except to maybe say two things, that there are some new DRGs that stand out compared to the previous plot. And the other thing is that the cell for psychosis, whereas in the previous one, you know, it was this one, it didn't really look all that different from the other ones, although it does have a little spike on the left. But in this one, it looks like no other cell. You can look at all the other ones, and it has these two horizontal stripes. There's like both. Anyway, I won't go into the details because of time. All right. So we've covered some more stuff from our diagram, but we've really only looked at hospitals and DRGs, and we haven't looked at geography. So I want to show a little bit about geography, but I'm not going to go into the same amount of detail as for the rest of them because, what, it's 8:15 now already? But of course, you know, you have geographic information. You can take some of these properties that you've computed for various geographic units, and you can put them on a map to begin with. So let's switch to that here. So these are some, you know, standard choropleth maps. You are going to quickly find out that there are problems and limitations with maps. Like, you can't really show more than one property at a time. To show multiple properties, you have to make multiple maps. It becomes difficult to compare. You pretty much immediately have to pull in population data in order to normalize by population, because right now, see in the top ones, you see the large states stand out. So yeah, the bottom ones are normalized by population. But anyway, there's lots of problems with it. Our regular host here, John Shaw, he actually did a whole talk just about problems with maps a couple months ago. So another kind of plot that you might try and use for exploring geographic information is to actually do a scatter plot of whatever your geographical units are. So this is a plot of states, and it lets you compare them a lot easier and so on. So I'm not going to go over the insights that I found with these plots. I actually did find some insights, but I'll actually touch on those with a different kind of plot because I really want to show you that one. So let me switch back to my presentation again. But here's kind of what those ones cover. And one of the things with the kind of plots that we made so far is that they kind of focused on one kind of entity from our relational schema, maybe two at times, but we've always had to aggregate over the third type of entity. So the final plots that I want to show you, and there's really only two more things left, are sort of integrative visualizations, where I'm going to try and pull in all three kinds of entities. So let's do that, and I'm going to go to here. All right. So let me explain what we're seeing. Every line is a state, and there's a bunch of yellow bars. Each bar represents a hospital in that state. The width of the bar is the number of discharges for the hospital. You have this nice hovering, you can see where they are and a whole bunch of other information. The coloring is the one that we've seen before. There's actually a legible legend here. Red is dedicated hospitals, orange specialized, yellow generalist. And then on the left-hand side, we have a whole bunch of controls to help us look at the information in different ways. So you can sort stuff. Right now, the states are sorted by population, by Medicare population, so not overall population, but actually just the people enrolled in Medicare. And then within each state, you can sort the hospitals. And right now they're sorted by number of discharges, so basically by size. So they go from large hospitals to small hospitals. So what it kind of immediately shows is, because the red is on the right, what does that mean? Well, it means that dedicated and specialized hospitals tend to be small. But every now and then something pokes out. There's like an orange one here in New York. It's a hospital for special surgery. It does 8 different DRGs. You're going to notice a lot of 400 codes there. This is kind of confirming that hypothesis we had, that those diseases, they're actually being handled pretty much by the same kind of hospitals. But anyway, it does 4,000 discharges for just 8 DRGs. If you look at its neighbors, they also do about 4,000 discharges. They come from like 80 different DRGs. So that's a huge surgery hospital over there. There's also a red bar here that stands out in Massachusetts. It's dedicated to one DRG. 897 is alcohol and drug abuse. So we have here the DRG combo box. I'm actually going to switch to that DRG because it really stands out. It's going to take a second here to refresh. There you have it. Okay. So it does more than half of the discharges in the state of Massachusetts for alcohol and drug abuse. And in fact, the states are still sorted by Medicare population. It does 3 times the discharges that the entire state of Texas has. That's a lot. If you look it up, you actually find that it attracts some patients from the neighboring states in New England, but New England, it doesn't really have that much larger population by itself. Even if you put New York, I don't know that you're going to top Texas in terms of population. So kind of interesting stuff. So this visualization, here's just for reference, you don't have to worry about all of them. It's more of a visual thing. The amount of dark blue here is how many properties we touched with that one visualization from our data diagram. So I want to show you one last plot that it's also an integrative visualization, but it's a very different one. Because it looks at the data as the graph, as the relational data that it actually is, right? Okay, after all, it's relational data, we should try and look at it as a graph. Let me quickly explain what you're seeing here. There's a bunch of dots over the top. Those are hospitals in Massachusetts, so this plot is only for the state of Massachusetts. The dots on the bottom are DRGs, their diagnoses, and there's a link whenever a hospital handles a DRG. And the width of the link is what percentage of the hospital discharges for that DRG, and the color is how prevalent the DRG is. They're also sorted left to right, so hospitals are sorted going from specialized on the left to generalist on the right, and DRGs are going by coverage, basically. The ones on the left, not a lot of hospitals do them. The ones on the right, a lot of hospitals do them. So there's like 3 thick bars here that stand out. They basically show that there's a bunch of either dedicated or general or specialized hospitals that treat diseases that are actually fairly well covered. They're also fairly prevalent. Like these lines are dark red and dark orange, so those are prevalent diseases, which is kind of interesting, right? You have hospitals that specialize in diseases that are very common but also very covered. One of them is actually the alcohol and drug abuse one. So, once again, a very property-rich visualization, and here's what we've covered overall. So, I'm hoping that by this point I've convinced you that there was a lot of stuff in those 4 columns of data. But it's time to wrap up, so here are my take-home messages. Don't underestimate what the data can tell you, okay? It's small, but it could be very rich. Don't overestimate what the data can tell you, right? It pointed us to a lot of facts, but it couldn't explain them for us, okay? Observational data usually cannot tell you why you're seeing something. So I'm gonna, also use multiple visualization perspectives. We've seen that over and over. It helps you get a really good understanding of your data. Do plan on spending a significant separate amount of time to communicate results in addition to the exploratory efforts. And use whichever tools you know best. My message here was really about the process, but do be mindful of reproducibility. With that said, if people aren't too tired, I actually can talk about the tools. I'm going to do at least one slide about the tools, okay? For most of the static plots that you've seen, these are basic packages, graphics, lattice, maps, nothing too fancy. For the interactive visualizations, I use the library, an R library called Shiny. It basically helps you make web apps from R. I don't know any JavaScript or any other kind of web programming. All of those that you've seen that I was doing all the hovering, the combo boxes, all that stuff was written from R. Actually, the hovering in the plots comes from the Google Viz library. That's also an R library. It helps you make interactive charts, and it grabs the Google Charts JavaScript API for you, is what it does. For the graph stat plots, I'm going to mention Gephi because it's actually my go-to tool for visualizing networks, but the one that I showed you was actually not made with Gephi because that layout that I showed you is actually an instance of something called a Hive layout. This is something that a guy called Martin K. At the Genome Sciences Center came up with, and it's a very cool way of visualizing charts. But Gephi didn't have a layout plugin for it. So that one I actually implemented from scratch in R. I just put a bunch of dots and a bunch of lines to make it. So I can, who here wants to see R code? A few people. Okay, the ones that don't, I guess. Okay. So I'm actually going to start with, I would ask though the ones that don't care to maybe keep quiet, because my voice is running out. So the way that you, by the way, Shiny has a great website, great tutorials, it's very easy to learn. The way you make one of these apps, okay, you create a folder and you need to have in it 2 files. One is called UI.R, the other one is called server.R. Pretty intuitive, right? So I'm going to show you the ones for the last interactive app. I showed the one with the bars. So first, the UI file basically is the one where you are going to define some of those controls that you want your user to play with. So you put in things like, radio buttons, combo boxes, stuff like that. So Shiny basically has a whole bunch of functions to help you with that. So like putting a radio button is as simple as that. You give it a name. It also supports something like conditional panels. In that visualization, if I change one combo box, some of the other radio buttons, what they showed would actually change. So you can do some things like that. You'll see all sorts of functions that correspond to HTML tags. So you can, put nice text around your visualization and stuff like that. And then the actual chart is just this one line. Okay, you tell it render as HTML this object called gvis1, which is going to come from the server side. Okay. So let's move to the server side. On the server side, you have access to 2 things. One of them is a variable called input that gives you access to the values of all the controls you've defined on the UI side. Okay, so you can see input $state order, input $color type, and so on, that kind of stuff. You also have access to a variable called output, and that's where you're going to have your plot, and it's going to get sent to the other side. So there it is. We have to remember that gv1, think output.gv1 equal. And then here's where the Google Viz stuff comes into place. So right now I'm rendering a Google Viz chart. The Google Viz call is here. Okay, it's making a bar chart basically. You can also, you don't have to use Google Viz to use Shiny. There's other things like render plot and stuff like that, and inside it you can put any kind of function that makes a plot from the basic R libraries. The Google Viz ones, what they do is that they basically create a whole bunch of text that represents HTML and JavaScript. That's what they do. They create that for you, and it's going to get sent to the other side. So I'm going to just quickly uncomment this printout line here, and I'm going to run the app directly from R. So the way that you run it is you just say run app, and you give it the name of that folder where you put your two files. And what it does is it's going to start a local server. It's going to automatically open a browser window for you, and it's going to run the thing. So this is what you use when you actually deploy, when you actually develop the app. If you want to deploy it, you have two options. Shiny offers a Shiny server that you could download and install on your own machine, or they offer a hosting service. And this is actually what we used for these ones. So we got an account with them and we deployed our apps on their side. So now quickly, just switching back to R, I want to show you the output of that Google Viz call. This is kind of what it looks like. It's basically a whole bunch of HTML and all the data, right? Like it's a lot of stuff, which is why that particular chart was the slowest one to update. But I don't know, here's the header part of it. It's basically HTML with JavaScript inside it, and all the data inside it, and all the formatting and that kind of stuff. I think that's it. I'm done.
Anyone have any questions?
How many people think they're going to come for food and drinks afterwards up on Main Street? Okay, 15, 20? Yeah.
So it's Mr. Brownstone's between 13th and 14th, I think, on Main Street.
Question to yourself in the crowd.
Okay. Does anyone here know of a Shiny equivalent for the IPython notebook? Sorry.
I don't, I'm sorry.
Thank you.
You could. I don't know yourself. It'd be easy enough to hack it together with IPython's own primitives. You can basically return HTML cells or HTML values, and it'll just render them. So you just create a function that does what you want to do and stick it in there. Yeah, including using any other like D3, throw D3 in there.
Anyone else?